So in the last lecture we discussed about the characteristics of single degree of freedom system. We also understood how to write the equations of motion using 5 different principles: simple harmonic motion, Newton's law, energy method, Rayleigh's method, and D'Alembert's principle. As we said, D'Alembert's principle remains as a concept because D'Alembert's principle converts the dynamic problem to equivalent static problem at any given instant of time. So it is actually a concept and not a reality, and it can be successfully employed only for single degree freedom system models, because it is very difficult for you to understand on which modes what inertia force has got to be proportionately applied. So for single degree there is only one mode of operation, therefore it is easy for us to understand that this can be put for single degree freedom system model successfully. Now we pick up a single degree freedom system undamped free vibration model and see how to estimate the essential characteristic, which is fundamental frequency of vibration of this model. So we all understand that single degree freedom system model idealized spring mass system looks like this. So this is my f of t. I am measuring my x of t from the Cg of the mass. I am setting this to 0. I call this as free vibration. I am setting C to also 0. So C is set to 0. So it is undamped, and f of t is set to 0. So it is free vibration. So we already know the equation of motion for this system is given by mx double dot plus kx is 0. So we can say x double dot plus k by m of x is 0. So x double dot plus omega square x is set to 0, where omega square is k by m. So this is actually a second order ordinary differential equation. The variable is time, so it is a time variant problem. So I must write the auxiliary equation for this problem. I can say this is d square plus omega square is 0. So d square is minus omega square, or d is plus or minus omega. Therefore the roots are imaginary. So one can write so basically the root should be alpha plus I beta, that is x1 x2 should be alpha plus I beta. In my case the real part is 0 because it is not there. So the complementary function for a second order differential equation is simply given by e power alpha t of C1 cos beta t plus T2 sin beta t. We already know alpha is 0 and beta is omega from my comparison. So I must say x of t is C1 cos omega t plus C2 sin omega t. Now C1 and C2 are constants which should be eliminated. So at t equals 0, let initial displacement and velocity be x0 and x dot or 0 respectively. So substitute here and tell me what is your x of t ultimately, substituting for C1 and C2. So my x of t is C1 cos omega t plus C2 sin omega t. So, at t equals 0, x0 is the initial displacement I have here. So, that is equal to C1 because this function goes away. So, x dot of t is minus omega C1 sin omega t plus omega C2 cos omega t. So, x dot of 0, which is the velocity at t is equal to 0, the sine function goes away, it becomes omega C2. So, C2 is x dot of 0 by omega. Therefore, x of t as a full function will be x0 cos omega t plus x dot 0 by omega sin omega t. So, if you know the initial values of x0 and x dot 0, which are displacements and velocities at t is equal to 0, if you know these initial values and if you know omega, where omega is square root of k by m, which is a structural characteristic, it does not depend on the time variant at all. Remember, omega is not a function of time. If you know the stiffness of the system or the elastic restoring force constant, and if you know the mass of the system, which is the inertia represented value of the model, you must be able to work out omega in radians per second, where mass is given in kg and k is given in Newton per meter. So, if you know these initial values, I will be able to get the full. Let us try to plot this and see how does it look like. It is actually a simple harmonic motion with an initial displacement x naught. So, let me try to plot this. So, this is my function of time, this is my x of t, and this value is what I call as x0. So, pick up any successive peak and that is my time period of vibration, one full cycle. You can pick it up even in the negative peaks also, this is also t. So, x of t, as you see here, is a simple harmonic motion. That is the first observation what I see from this figure. The second observation is x of t is continuously present and it is not dying down. The value, the amplitude of x of t is constant, is continuously present for infinite t, whereas in reality when you try to displace the spring mass system and release the force, after any long duration of time, the response or the amplitude of the response will die down and it will come to static state of rest, whereas this figure does not show anything of that order. It means there is something which is missing in this figure or in this whole idealization, which is not really modeling the actual behavior of my spring mass system, because the spring mass system should come to rest after long cycles of operation, which is not happening from the analytical equation what we just now saw. So, the one which is missing is the damping, which is offered by the air or the resistance to the movement of this x of t. So, we must model the damping component to it. So, if it is an undamped system, I have not modeled the damping component. So, the absence of damping component gives unrealistic value of x of t, which is as shown in the equation here. I call this equation number 1. Now, let us set case 2. Let us say C is no more equal to 0. Now, the question is C is what we call as a damping coefficient or constant. There are two kinds of damping exist in the literature. Damping are of two types. The first type what we call as viscous damping. Okay, let us put it as Coulomb damping here. the second is viscous damping. There are special problems associated with these kind of dampings, we will see them in detail after this lecture is complete. So, there are some special features associated with viscous damping with the Coulomb damping, why they are actually not popular for fluid structure interaction problems, we will see that later. So, let us quickly understand what do we understand by or what do we mean by Coulomb damping and viscous damping. Coulomb damping is a resistance offered or the damping force generated because of friction. Coulomb damping offers damping force generated because of friction between two surfaces. Now, you may wonder where are the surfaces coming in, can I have friction between the liquid surface and the solid surface. Interestingly, let us take up a structure or a leg which is connected by a specific joint using a special. Okay, this is a joint. The diameter of this member and the diameter of this member are different, and the boundary condition of this member and the boundary condition of these members are different. The load subjected to this member and the load subject to this member are different. It means the behavior of this member under the combination of load is different from this. Therefore, there is always a possibility that at this joint there can be relative movement between these two members. So, that relative movement can offer frictional resistance. So, frictional resistance need not always arise from fluid and the structural interaction, it can even come within the members also. So, this can also resist the damping or it can offer resistance to the response of the system because it can dampen, can reduce the response. So, the damping force in Coulomb damping is generated by friction between the two surfaces. So, it is actually equal to the normal force multiplied by the coefficient of friction between the two surfaces, that is how it is estimated. It is interesting to know that this force is independent of velocity. Though you may wonder that because of the relative movement between the two members at this junction, frictional force is generated. So, that movement should have a capturing value of its displacement and velocity, but that movement will be very minimum compared to the overall global movement of the structure. So, it is independent of velocity, it depends on the normal force acting on the member and the coefficient of friction between the two surfaces which are sliding one against the other. So, it is independent of velocity, and this is how the damping force is given, is a normal force, it is a normal force multiplied by coefficient of friction between the two surfaces of the material which are sliding against each other. We look at the viscous damping. Viscous damping is function of velocity. The damping force the viscous damping accounts for the viscosity present in the system, So, the damping force in this case will be proportional to the velocity, or it can be equal to some constant of the velocity, and this constant is called the damping constant, whose unit can be Newton per meter per second. Okay, that is the unit of this damping constant C. And this is a very famous method of damping adopted in offshore structures or ocean structural system, because we deal with fluid structure interaction and viscosity will be present in the system, and therefore our damping proportional to velocity. Being a fixed base structure, still we will have velocity of the body or water particle. If it is a compliant structure, we will have relative velocity between the water particle and the structural member. So velocity will be predominantly present in both the cases. Therefore our model of using viscous damping for structures or models which has fluid structure interaction is more relevant compared to that of Coulomb damping. Okay. So we will be generally using viscous damping models in our ocean structural systems. That is the reason why we are using this, because FSI deals with the component of velocity present predominantly in the system. You may wonder that in a fixed base structure how the velocity of the structure is important. I am saying the water particle velocity will be anyway important. So the velocity will have a dominant role to play, which can offer a damping value. So in the last example, that is which is undamped free vibration model, we already saw that the response of the system is continuously present, which is unrealistic, because there will be some damping offered by different sources. The response will die down even after a long duration of time, but the analytical equation does not reflect this characteristic in my solution. To incorporate that, now we should say that let C not be equal to 0, but let f of t be still remain 0. So I am still doing now a free vibration analysis or a free vibration response for a damped system. So I am looking now for a damped free vibration analysis. Any questions here? Any questions here? Any doubts? So now let us write down the standard model once again. The spring mass system whose mass is known, I have elastic restoring constant which is K, or the stiffness of the system, and now I have also a dashpot which is the damping constant given in the system, and of course I can apply f of t here and I can apply x of t here. You must understand there is a very great similarity in all the problems or all the derivations I am doing. I am measuring the coordinate of displacement of the mass only at the point where the mass is concentrated. I could measure the displacement coordinates anywhere at my origin, anywhere I can measure. Okay, I am not doing that. I am always measuring the displacement coordinates only at the CG of the mass or where the mass is lumped. I am also applying the force only at the point where the mass is being. I can also pull the spring, I can push the spring from here, I can move the support, I am not doing them. It means in general I am using the displacement coordinates and the force coordinates at the point where the mass is lumped. Okay, that is a very important point. We will violate this and see what happens later in multi-degree freedom system models. So this is a single degree freedom system model, because the model is constrained to move only in the horizontal direction that you see here. The model can neither jump, the model can move normal to the board. Already we discussed in the previous lectures how we are preventing by putting an additional constraint in the normal to the board, and the mass cannot move in the other fashion. So it is only in 1 degree. So if I use Newton's law, let us say these are my restoring forces which is K and X, and this is again Cx dot. I am using a viscous model here. So I should say minus Kx minus Cx dot should be mx double dot, because that is my mass into acceleration force as per the Newton's law. So I will get mx double dot plus Cx dot plus Kx as 0. The 0 indicates it is a free vibration study. The presence of C indicates that it is an damped system, and this is my inertia component, this is my restoring force component, which will be always present in all the systems. I am rewriting the same equation back again here. So mx double dot plus Cx dot plus Kx is 0, divide by m, So, x double dot plus c by m of x dot plus k by m of x is 0. So, x double dot plus c by m of x dot plus omega square of x is 0, where omega square is considered as k by m. So, d square plus c by m of d plus omega square is 0. That is my auxiliary equation for this second order ordinary differential equation. So, I can simply write minus Cm plus r minus root of b square minus 4 omega square whole by 2 will be my roots alpha 1 and alpha 2. So, I will just modify this once again. So, alpha 1 and alpha 2, which are the roots of my equation, can be minus c by 2m plus or minus half root of c by m the whole square minus 4 omega square. This can be further minus c by 2m plus or minus root of, if we take it inside, c by 2m the whole square, because this 4 comes here, and minus omega square, because this 4 will get divided. So, these are my roots now, alpha 1 and alpha 2. I will remove this. So, for the roots to be real and distinct, I must have x of t as for the roots to be real and distinct. So, I understand from here alpha 1 will be minus c by 2m plus of this value, and alpha 2 will be minus t by 2m minus of this value. So, the roots can be distinct, can be real, because there is no imaginary component in this. So, the imaginary component come into play depending upon what would be the value of these two relatively. If this value is higher, then the root can become imaginary. If this value is higher, the root can become positive. So, we really do not know whether the roots will be real or distinct. It means to understand this roots more in detail, I must work on this part mathematically, what we call as discriminant of this equation. Let me pick up this. So, I am looking for what we call in the literature critical damping. Critical damping mathematically says set the discriminant to 0. The moment I do that, when I set this discriminant, the argument inside this parenthesis is called discriminant. If I set this to 0, the roots will become real and equal. Okay, they are not distinct, because both the roots will be minus c by 2m, because this is going to be 0. But I want to pick up that first and see what happens. So, c by 2m the whole square minus omega square is set to 0. So, c by 2m the whole square is omega square, c by 2m is omega. So, I say CR is 2m omega. I am using the CR saying C critical. Is 2m omega. Of course, this equation was 2. One can also expand this slightly because omega is known as root of k by m. So, CCR can be 2m root of k by m. I can say this as 2 root km, okay, that is also there. Some literature will give you CR as in this format, it is one and the same. Already we know omega is root of k by m. So, one can write in either form. Since the discriminant is 0, now the roots are real and equal. Now the roots are real and equal. Therefore, x of t can be simply said as a plus bt of E alpha t where alpha in my case is CCR by 2m. So, CCR by 2m, therefore, x of t can be a plus bt of E CCR by 2m of t. Minus, okay. The root is minus c by 2m, is it not? The roots were alpha 1, alpha 2 were minus c by 2m plus or minus, oh, this is 0. So, there is minus here, right, there is minus here. So, this indicates very simple, this is my fourth equation I am having. This indicates some inferences to me. Of course, A and B are constants which can be eliminated depending upon initial conditions, based on initial conditions, as we used some initial conditions in the last example. Same way at t is equal to 0, x 0 and x dot 0 can be displacement velocities, I can use and substitute them and I will get A and B. I need two conditions because there are two constants, I can use them. The most importantly, the moment I introduce damping in the system, you will see that the response is decaying exponentially. This is very important, the response decays because minus exponentially, because it is e power minus, so it is decaying exponentially, which is a realistic value, because the response will die down after some instant of time or after some span of time, which is happening from the equation number 4 as shown here. Whatever may be the initial condition, whatever may be the values of A and B, it is very clearly understood that at a long span of time and after some time t, you will be keep on decreasing, and at one given point of time x will become 0, okay, which was expected in the original behavior, which was not reflected in the earlier equation of free vibration response where undamped system was shown. So, damping is an inherent component of my single degree of freedom system model, I cannot eliminate it because it shows me an unrealistic behavior otherwise. So, I have to include damping, and in this model I have picked up viscous damping. I will speak about Coulomb damping slightly later once I complete this experiment or this exercise, okay. So, as I said, why we are using Coulomb damping in ocean structural systems, because we have got lot of interest towards viscous application in this FSI models, therefore we are using it. Does not mean that we cannot use Coulomb damping, there are some difficulties associated with Coulomb damping, we will see that. Any doubt here or anything to be added to the inference from this equation? Are we all getting it, how we are getting x of t so far? There is no confusion, right? So, if you look at this equation, you will see there is minus c by 2m here, the original, I have rubbed it off. So, minus is there, means that minus here, alpha will be negative. Instead of c by 2m using CCR by 2m, because I am calling this as critical damping, I mean name given in the literature. Okay, remaining I am not changing anything, I am using the same equation back. Any doubt? Shall we proceed further? Now critically damped systems have some demerits. We have seen only one case in the discriminant, setting it to 0. Discriminant may not be set to 0 also. Okay. So let us do the remaining two cases also. Discriminant can be negative, it can be positive also. So let us see the remaining two cases, then we will dialogue on what would be the comparison between critically damped, that is D0, D negative and D positive. We will compare them possibly in the next lecture. So now we will take away. Now when D is not 0, that is case B, the discriminant not set to 0. Case A was discriminant set to 0, we have argued and we got the value. Now I do not want the discriminant to set to 0. So under this there are two cases, discriminant can be negative, it can be positive. We will take discriminant negative, that is discriminant is negative. What does it mean is, let us write down this equation, C by 2m the whole square minus omega square, that is my discriminant. Okay, this is my discriminant. C by 2m the whole square minus omega square is less than 0, negative. So I will call this as underdamped system. So I call the damping constant as less than that of C critical because it is underdamped. So the damping constant will be lesser than the critical damping. Obviously one can expect if we put discriminant as positive, I call that as overdamped system and I understand that C will be greater than CCR and the discriminant will become positive. Okay. In this case discriminant is negative, I am classifying it myself, I am taking it, let be negative, there also it is let D be 0. Okay, that all we are setting it, we are imposing a condition, it is not happening by itself. Okay, we are setting a condition and seeing what is happening to my solution procedure. So in that case I call this as underdamped system and my damping constant C will be lesser than CCR. So I should say that C will be lesser than 2m omega because already we know CCR is 2m omega, CCR is 2m omega, we already know this. So let us pick up the discriminant D, slightly modify this, is going to be C by 2m the whole square minus omega square. I can modify this as C by m the whole square minus 4 omega square, or I can say minus of 4 omega square minus C by m the whole square. So I can rewrite this as I square of 4 omega square minus C by m whole square. So I will take away this. Now we already know that C is less than CCR or C by 2m omega, that is nothing but CCR, I consider this as a ratio called zeta. This is called damping ratio. So getting it back, d discriminant d will be I square of 4 omega square minus c by m. So I should say 2 omega zeta the whole square, okay, that is 4 omega square zeta square. Is that okay? C by m is already here. So c by m is 2 omega zeta. I have a square value, here. Substitute that, I get 4 omega square zeta square. So now simplifying, I can say I square 4 I square 4 omega square 1 minus zeta square, that is t. So alpha 1 alpha 2, which are my roots, will be minus c by m plus or minus root of d, that is discriminant, divided by 2. Now substitute back and tell me what are your alpha 1 and alpha 2. So I get alpha 1 alpha 2 as minus c by 2 m plus or minus. So if I take a root of this, I 2 omega, 2 goes away, I omega 1 minus zeta square. Is that all right? Okay. I call this as omega d, where omega d is called damped frequency. So now I can say alpha 1 alpha 2, which are the roots, can be minus c by 2 m plus or minus I omega d. So this is my real part, this is my imaginary part. Now I can write a complementary function for this second order differential equation as e to the power of alpha t c1 cos beta t plus c2 sin beta t, where the roots are expressed as alpha plus or minus I beta. Alpha is the real part and beta are the imaginary part. Substitute back, write the equation x of t. So what is x of t? X of t e to the power of minus c by 2 m of t c1 cos omega dt. So x of t e to the power of alpha is minus c by 2 m of t c1 cos omega dt plus c2 sin omega dt. That is my equation number, is it 6? 5. Now again there are constants c1 and c2 which are in this equation, which can be eliminated by providing some initial conditions. So c1 c2, remember the c1 and c2 are not damping constants. If you are confused with the term c, you can use it a and b also. C what we are using here is a damping constant or coefficient. Okay. C1 and C2 are some constants for the differential equation. If you are confused with the term C1 C2 with respect to C, say them as A and B, that is up to you. Okay. So C1 and C2 are the constants, can be eliminated based on some initial conditions. We can apply some initial condition, we can eliminate them, we can estimate them, right. What I see here is the moment I introduce damping, when C is not 0, the response of x of t is again exponentially decaying. Okay. Because of this term, e to the power of minus C by 2m of t. So it is exponentially decaying, which is again a realistic representation of the behavior of the spring mass system under free vibration. Now I want to explode this response in detail and see actually what happens, how this response looks like on successive peaks, because that is very important for me to estimate the value of damping. Let us see how do we do that. Any questions here? Any doubt? Generally, if you look at dynamics books, all the references given in the website, all of them talk about the structural dynamics, and in all structural dynamics books these preliminary derivations are given. Very few books will make it clear to understand. I am sorry to say this, but that is a fact, very few books, and most of the books will skip many of the sequential steps, which is very dangerous for a person to understand. The moment you do not understand the sequence of steps being followed, either you will skip reading that or you will feel sleepy, either thing will happen. Okay. And it will result to a very interesting phenomena that you will start memorizing things. The moment you are memorizing, because we have extraordinary memory and remembrance capacities which has been generated by a very good diet system and sports systems, so we are not able to reproduce at any given point of time, in particular during the examination, very badly during comprehensive, and very badly during interviews. I mean, they will ask something, you will be telling something else, and since there is a mathematics flavor available here, people are extraordinarily brilliant in mathematics. So therefore they have a very strong affinity towards, love and affection towards mathematics, so they develop a very inbuilt fear for memorizing or remembering these equations. With that fear, if you open any book and try to understand, sir, can I understand the derivations again, you will never. If you want to understand them, you must understand them again by your own handwriting from the beginning. Start from writing equation of motion and start doing it on your own. The best thing is this only, any time during your life till your death somebody asks you what would be the characteristic of my undamped free vibration or forced vibration system, derive it from the beginning and then tell what it is, because then only you will understand many things we have been discussed in the blackboard will come to your memory. This is what I have practiced. So I am making it compulsory that I am deriving it on the board. I could have also projected in a PowerPoint and showed you only the equations. Okay. So we will have the same extraordinary super flavor which you have been having earlier, which we will try to continue to have in future from the respective people which you will meet or whom you will meet. So that is, it may look very simple, but once you do it without my assistance you will find the vulnerability on these equations. It does not stop here, it has started here, it will go further, deeper and deeper, it will expand horizontally and vertically. You will understand the gravity of the problem once you move deeper and deeper. It has just started. Okay. So there is a problem, you will not be able to appreciate it. We have got only 5 minutes, I do not want to hurry up this discussion. It is a very important discussion for me, it is a very important discussion, I do not want to hurry up about this equation, because I want to look into the successive peaks in this decay, and then I want to derive what I call the damping ratio from this, and I want to speak about the experimental validation of these data in reality. So I do not want to hurry up in couple of minutes. So I prefer to stop the lecture here. I will continue in the next class, no hurry. If you have any questions, I will be happy to answer. If you do not have questions, I have some very strong recommendation for you. Whatever derivation we have so far done, we have done only for 2 cases, rather second case A and B. So if you consider that as 3 cases, okay, it is 3 cases. Rederive them again, then follow any one book of your choice, any one book. You can pick up the book at random also, because all books will speak about this. All books on dynamics will talk about this, which are available in the references, any one book. Also look into any one research paper which addresses dynamics of offshore structures and see, are you familiar with the terms being used in that paper. Parallelly do this, because in the papers they will talk about viscous damping characteristics, some papers talk about the initial conditions, some paper talk about the damping ratio, depending upon what the author is addressing. So start reading them parallelly, okay, because every paper on dynamics will talk about free vibration, okay. So read them parallelly and try to understand and follow one book at least, and then if you have difficulty in the next class, sir, you have done something wrong, there is no minus there, the author says it is plus and the author has explained why it is plus, we will again rediscuss them here, revisit them here, because in my opinion I think I have not done any mistake, but if you feel there is a mistake done, we will revisit again this derivation in the next lecture, otherwise we will proceed further for more interesting mathematics coming up in the next lecture. So any doubt, any questions? Stop it. Thanks.